So in this video what we want to do is establish the parametric form of the derivative. So what we need to remember to do this is how a derivative's been defined. So remember from Calc 1 when we initially defined derivatives we took the limit of the difference quotient. So we said, hey, let's take the limit as h goes to 0 of f of x plus h minus f of x all over h. And what we want to understand is that this is one of many forms that the derivative can take. We want to recognize that the numerator is actually a change in y, and the denominator is just the change in x. It's the slope of the secant line between 2 points. So if I have a point, 2 points, and I establish that secant through them, the secant line going through those points, all we're doing when we find the derivative is finding the slope of the secant line and then taking the limit as delta x goes to 0, so that instead of a secant line we wind up with the tangent line. So we really are saying, hey, we need to take the limit as delta x goes to 0, and we can write this in a lot of different ways. We can say, hey, let's take y2 minus y1 over x2 minus x1. We'll take the limit as still as delta x goes to 0 because x2 minus x1 is just the change in x. And in fact, in the difference quotient, all we did is give x2 minus x1 the name h. So this really up here is x2 minus x1 or delta x. So the derivative is just the limit of the slope of the secant line as the delta x term goes to 0. So what you want to think about is, what's going on if you've parameterized things. So if you know that you have parametric functions giving you the points on the graph, x of t, y of t, x and y have both been parameterized. If you know the ordered pair here, x of t at some time t and y of t at the same time t, then this point up here is just going to correspond to x of t plus h, where h is the change in time between those 2 points. It's a delta t if I use it in this context. So you'd have a x of t plus h, the time here plus the change in time it took to get to the second location, and y of t plus h, where h is that change in time. So if you wanted to calculate the limit as delta x goes to 0 of delta y over delta x to get the derivative, then we could just take y of t plus h, here's the second y coordinate, here's the first y coordinate, minus y of t. There's delta y, described in terms of the parameterized variable. And then our change in x, our delta x, would just be given by x of t plus h, the second x coordinate, minus the first x coordinate. And what would make delta x go to 0? Well, letting h go to 0 would let delta x go to 0. So this, we could really say here that this statement is equivalent to taking the limit as h goes to 0 of this ratio, because as h goes to 0, x of t plus h approaches x of t, making delta x, the change in x, go to 0. And then what you can do here is just multiply by a sneaky form of the number 1. You can say, hey, I'm going to do 1 over h divided by 1 over h. I can multiply by 1 over h divided by 1 over h because this is just equal to 1, and then distribute the 1 over h here into this numerator and distribute the 1 over h here into the denominator terms. So I wind up with the limit as h goes to 0 of y of t plus h minus y of t over h divided by, and down here in the denominator we would have x of t plus h minus x of t, and we would get over h here. And then we want to recognize that what I have here really is just the difference quotient. We're taking the limit as h goes to 0 of a difference quotient applied to the parameterized y and a difference quotient of the parameterized x. So this really, if you're taking the limit as h goes to 0 of the difference quotient, that is the definition of the derivative. So we notice up here you wind up with y prime of t, and you wind up down here with x prime of t, and y prime of t we could also write that as dy dt, would still be y prime of t, and down here x prime of t could be rewritten as dx dt. So this gives us the way to calculate the derivative dy dx in terms of the parameterized functions. So we get dy dx is dy dt divided by dx dt. So we formalize that on this slide. Hey, if you have parameterized equations, you can calculate dy dx by taking the derivative of y with respect to t and dividing it by the derivative of x with respect to t. And then you can extend this to higher order derivatives easily just by applying this principle repeatedly. We can repeatedly apply this. So if I wanted the second derivative, I recognize that the first derivative is d dx of y, and then we got, hey, let's take dy dt over dx dt. dy dt, another way of saying that is d dt of your parameterized y. Well, here, if we're taking the second derivative, we would do d dx of dy dx. Remember, dy dx is just y prime from this previous result, in the sense that y prime with respect to x, so dy dx, and we would take d dt of the numerator. Remember, when you do dy dx in the parameterized form, dy dx is going to be a function of t. It's a function of t, so you repeatedly apply this theorem, and you say, hey, this guy right here, he's really y prime. I want to know the derivative of y prime. So take the time derivative of y prime divided by x prime of t, or dx dt. So this principle just extends. We could do the nth derivative, would work out the same way. If we had dn y dxn, the nth derivative, then we would just take d dt of the previous derivative, dn minus 1 y over dxn minus 1. So we could extend this into to the nth derivative, whatever derivative we want to take.